Hey there, Coach Owings here from Frisco High School. We're on page 3 talking about counting and types of probability. So a definition real quick to start is that the sample space is the list of all possible outcomes in a probability model. So we want to list the different outfits we can make if we have a red, green, and blue shirt, and a pair of green, blue, navy, and apparently mint is a color shorts. So we can type all this out. We can have a red and a green. So we have a red shirt and green pants. We have a red and a blue. We have a red and a navy pants. We have red with mint pants. And we can do the same thing with the green shirt and green pants. Maybe for a dress-up day, you can do the green shirt and blue pants, so on and so forth. Maybe I'll cut this out and just jump straight to the end. Three, two, one. So then it asks how many total outfits were there. So we got 4 here, 4 here, 4 here. So we have a total of 12. And we can notice is that we have 3 shirts. If we multiply that by the 4 pants, that gives us our 12 outfits. And what we have just explored there and determined is the fundamental counting principle. It says if one event can occur in m ways, a second event can occur in n ways, the number of ways the 2 events can occur is m times n. So we can just multiply those 2, and it can be extended to any number of events occurring in sequence. So if we had shoes to add or other accessories, then we can just keep multiplying to get the different number of outfits. And you guys know this very well and have seen this multiple times in your math career and otherwise. So we got a question here. The access code for a car security system consists of 4 digits. Each digit can be a number between 0 through 9. How many possible codes are there when? And then we got A, B, and C. I do want to talk about 0 through 9 really quickly. So 0 through 9, if we think about it, and we have all those options, and we think about how many options it is. You know, we have 0 through 9. Some people might think that that's 9 options, but really we got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 4 options. That's 6 options for a total of 10 options. So when I say 0 through 9, I'm really thinking 10 options there. If I said 1 through 9, that would be 9 options. So similarly, if you got like 00 through 99, that's going to be 100 options. If we got 01 through 99, that's only going to be 99 options. And, you know, sometimes I tell my students, if you're having trouble with it, it's like smaller numbers, just count. So if we got, let's say, 4 to 8, you know, we might think really quick, 8 minus 4 is 4, but really that's 4, 5, 6, 7, 8. That's 5 different options that we got there. So with that in mind, let's go answer some of these questions as I erase all my sketching here. So hopefully you didn't write all that down. Sorry if you did. And 3, 2, 1. So let's answer these questions. How many access codes are possible when each digit can be used once and not repeated? So if we're looking at it once and not repeated, then we're not going to have any repeats. So that'll change our number. So our first digit there is going to be anything 0 through 9, which we've already said can be 10 different digits. One of those digits is going to be used in the first digit, so we take away 1. So how many do we have remaining? That'll be 9 digits, and then we keep subtracting 8 and then 7. So we're going to multiply each of these. So we have 10 times 9 times 8 times 7. For a total of 5,040 codes possible. What if each digit can be repeated? If each digit can be repeated, then we're not going to be subtracting 1. We're just going to take 10 times 10 times 10 times 10, which seems to be a 1 with 4 zeros, or 10,000 codes. And then part C, if each digit can be repeated, but the first digit can't be a 0 or 1. So this first digit now can only be 2 through 9. So that's going to be 8 possible choices. But then we have as many options as we want, all 10 options as we want for the remaining digits, for a total of 8,000 codes. All right, let's move on to the next page, get some more definitions on page 4 here. So we've just looked at is classical probability, where, let's make it a little bigger for you. 3, 2, 1. Classical probability, where each outcome has the same probability of occurring. And so we're going to say this is an event E. So our formula for the probability of outcome A, or our success happening, is the number of outcomes for A in event E out of, and we're going to divide that by the total number of outcomes in event E. So let's practice that here. So you select a card from a standard deck of playing cards. We're going to find the probability of each event. So the first example, event D, is going to be selecting the 9 of clubs. So the 9 of clubs, there's one 9 of clubs out of all of our total possibilities for playing cards out of 52. So we have one option out of 52. And normally we'd ask you to reduce and maybe change that into a percentage or a decimal, just depending on the question. I'm going to leave it as a fraction right now. Event E, selecting a heart. So there are 13 hearts. So we can say that that is 13 out of 52, the total number of playing cards. We could also reduce that, or just figure out that, hey, hearts is 1 out of 4 different suits. So it's 1 out of 4 there. Finally, event F, selecting a diamond, heart, club, or spade. That's every option, so everything isn't included there. So we can split this up if we want. We can say, oh, diamonds is going to be 1/4, hearts is 1/4, clubs is 1/4, spades is 1/4, and we can add all those together, or we can just say that that is 4 out of 4, or 100%. Either way there. So before we move off this question, I do want to go over a standard playing deck of cards really quick. Hearts and diamonds, as you can see on here, these are red cards. Typical decks are used often when we're talking about probability, so it's just good to have a little rundown here. Spades and clubs, as you can see, are black cards. Are ace through jack, ace, king, queen, jack. Those are our face cards. And then there are 13 in each for a total of 52. Probably should have done at the beginning, but oh well. All right, let's talk about empirical probability.